This is Chapter 12 of Dynamics. We are continuing with Kinematics. So in this first question, we have a tugboat that is pulling a small barge, and we are given the force function of F equals 81,000 minus 27,000 times velocity. Combined weight of 3,600 kilonewtons, and the two velocities of 1 meter per second and 2.5 meters per second. We are using the functions of the sum of the forces equals mass times acceleration, and our acceleration equals the derivative of velocity. We're being asked to find the time required to increase the speed from 1.0 meters per second to 2.5 meters per second, and then determine the distance traveled during that time interval. So we draw a free body diagram. We know that it is moving to the left, so we set our positive coordinate system that way. And from there, knowing that we have the combined weight of 3,600 kilonewtons, we determine the mass as we divide that by gravity of 9.81. We get our mass, and then using the function that we were given earlier, we know that force is equal to mass times acceleration. Setting that equal to the equation that we were given, we're able to find the acceleration. We're able to get this function, ax equals 27,000 divided by mass times 3 minus v meters per second squared. Continuing on, to find part A, as we take our function, because we're trying to find the time, so we use dt equals dv over ax. So we use separation of variables, follow the integral, and we're able to get the function of mass over 27,000 times the natural log of 3 minus v from 2.5 to 1. Plugging in those values, we find that our time is equal to 18.84 seconds. Following a similar pattern of using separation of variables and then integrating for part B to determine the distance, we find that the distance traveled is 36.14 meters. Moving on to the second question, we're given a truck that is attached to a pulley system with a boulder on a steel plate. Again, the acceleration is moving to the left. So we're trying to find the horizontal force between the tires and the ground, and the force between the boulder and the pallet. We're given specific values for the truck and the boulder and the pallet, and the acceleration of the truck. So using our kinematic equations and free body diagrams of the truck and the boulder, we are able to get the masses of the truck in slugs, and also the mass of the pallet and the boulder. Again, using equilibrium equations, we're able to find the tension of the wire at 609.32 pounds. Now, using this information, we're able to plug it into another kinematic equation to find the horizontal force between the tires and the ground between the truck and the ground. And plugging in our values to this equation, F equals the mass of the truck times the acceleration of the truck plus the tension, we're able to find that the force, the horizontal force, is equal to 765 pounds. Using our second free body diagram and using a similar approach, we're able to plug in our values that we know and that we were given, and the force between the boulder and the pallet is equal to 1,016 pounds in the vertical direction. In our next question, we have a tether ball that is spinning around in a circular motion. And we're being asked to find the angle of the cord that the cord forms with the pole, and also the tension of the cord. Again, using free body diagrams and our known equations from kinematics, setting an equilibrium point, we're able to find the tension of the cord, and using that, we're able to plug that into the summation of the forces in the x direction equation. Plugging that in and running that through algebraically, we end up with a quadratic formula, or quadratic equation of cosine squared theta plus 0.9061 cosine theta minus 1. Plugging that into the quadratic formula, we find that theta is equal to 49.9 degrees. And using that, we're able to find the tension in AB that we've solved for that equation earlier, and we get the tension is equal to 6.85 newtons. Next question, we have a wrecking ball attached to some equipment, and we're given the values. We're asked to determine the tension in the cable at the top of swing C and at the bottom of when the wrecking ball is at position D. Again, using free body diagrams and equilibrium and the kinematic equations that we know, we're able to set the mass times acceleration to velocity of the ball squared over rho. So using that and solving that algebraically, we find that the tension of the cable is equal to 122.2 pounds. That is at position C. Part B, for the position at bottom of the D swing, we again use free body diagram and our equilibrium equations, similar to step A. So we have the mass of the wrecking ball plus the mass of the wrecking ball divided by gravity times the velocity of the ball squared divided by the length of the wire. Plugging those in to our equation, we find that the tension at this point, at position D, is equal to 145.6 pounds. Next, we have a turntable and that is being used, and we also have a trunk on this turntable. We are being asked to find the coefficient of static friction between the trunk and the turntable. I haven't done this for a minute, so it was a little bit difficult at first, but knowing our kinematic equations, we find that the velocity is equal to 2.4 meters per second. Continuing to use free body diagrams and our equilibrium equations, we are able to find that, and setting these equal to each other, to find the static friction, we have mu s times the mass of the trunk times gravity is equal to the mass of the trunk times the square root of the acceleration in the tangential direction squared and the acceleration in the normal direction squared. Solving this algebraically and plugging in our values that we know, we are given that the coefficient of static friction is equal to 0.236. In the next question, we are given the orbit of Venus is nearly circular with an orbital velocity of 126.5 times 10 to the third kilometers per hour. And we're given some radial distances, and we're asked to determine the mass of the sun and the acceleration of gravity at the surface of the sun. So using the equation that we know, force equals G times M over R squared. Manipulating that to something else that we know of mass times velocity squared over R, and plugging in our values that we know, solving for the velocity, we get 35.139 times 10 to the third meters per second. And using this, GM equals RV squared, we're able to find the mass, and plugging in our values to this equation, M equals RV squared over G. Solving that, we're able to find that the mass of the sun is equal to 1.998 times 10 to the 30th kilograms. And using a similar equation as above, we're able to find the acceleration of gravity at the surface of the sun. As we have G times the mass of the sun equals the acceleration of gravity. Gravity at the sun's surface times R squared, capital R squared. Plugging in these values and manipulating the equation to find the acceleration of gravity at the surface of the sun. Plugging in the values, we find that the acceleration of gravity at the surface of the sun is equal to 276 meters per second squared. Next, we have a particle of mass that is projected from point A and traveling velocity perpendicular to R naught. We have this equation, R equals R naught divided by 2 minus cosine theta. And we're being asked to show that force F is inversely proportional to the square of the distance R from the particle to the center of force at the origin. So using the equation that we are given, And using an equation from the book, we were able to manipulate the equations into something similar. And we find that our force is eventually equal to 2 times m times h squared over r naught times r squared. And we know that the mass and r naught are constants, so the force is inversely proportional to r squared. Next, we're given a satellite that is in orbit at an altitude of 19,110 kilometers above the surface of the Earth. We have a few equations that we can use that we are given by the book. We're first has to determine increase in speed required at point A to achieve the escape velocity and enter a parabolic orbit. Part B has to find the decrease in speed required at A to enter an elliptic orbit at a minimum altitude of 6,370 kilometers. In part C, we're asked to find the eccentricity of the elliptic orbit. So using the equations that we know and plugging in our values, we find that g times m is equal to 398.06 times 10 to the 12th meters cubed over seconds squared. Finding the radius at A, we find that that is equal to 25.48 times 10 to the 6th meters. As we're increasing in speed, we have to find the velocity of the circular velocity and the escape velocity. So using that, we use two similar equations, as we have the square root of gm divided by radius at A. So plugging that in for the velocity of the circular motion, we find that that is equal to 3.9525 times 10 to the 3rd meters per second, and our escape velocity is 5.5897 times 10 to the 3rd meters per second. As increasing in speed, we take the escape velocity minus the circular velocity, and we find that it is the velocity needs to increase by 1.37 times 10 to the 3rd meters per second. Continuing on to part B. We are given these two equations from the book, and manipulating them and plugging in the values that we know, we're able to determine the height at 82.230 times 10 to the 9th meters squared per second. And plugging that into our V naught equation as h over r plus h naught, we find that initial velocity is 3.2272 times 10 to the 3rd meters per second. Using a similar solution to part A, our velocity is equal to the velocity, our circular velocity, minus our initial velocity. So the decrease in speed of the satellite has to be 725 meters per second in order to enter an elliptic orbit at a minimum altitude of 6,370 kilometers. Continuing on to part C for the eccentricity, using the equation from the book of 1 over r equals g times capital R squared over h squared times 1 plus epsilon cosine theta. Manipulating that to find epsilon, and then plugging in our values that we have calculated in parts A and B, we are able to find that the eccentricity is equal to 0.333. Moving on to the final question. We have a satellite that is in an elliptic orbit about a planet. We're not given any values, but we know that the distance from the planet to point B is r1, and the distance from the planet to point A is r0. Using these two equations that we already know, and also the equation that we used in the previous question of 1 over r equals gm over h squared plus c cosine theta, as we are given this equation, 1 over rho equals 1/2 times 1 over r0 plus r 1 over r1. We're asked to find the curvature of the orbit at each of the 2 points so that it can be expressed as this equation. So setting r0 is equal to RA and r1 is equal to RB. We plug them in and we're able to get these two equations. For theta b, we know is equal to theta a plus 180. And using what we know, we can plug in cosine A is equal to negative cosine theta B, and vice versa. So plugging in equation 3 into equation 1, we end up getting C cosine B is equal to negative 1 over radius at point A plus GM over h squared. Plugging that into equation 2 and then solving that, we find that 2 times GM over h squared is equal to 1 over radius B plus 1 over radius A. Using our force equation and manipulating that, in also what we know, we're able to find that the force is equal to m times h squared over r squared rho. And GM is equal to GR squared, which is also equal to h squared over rho, which then we are able to find that the curvature can be expressed as 1 over rho equals 1/2 times 1 over r0 plus 1 over r1. Thank you.